Alejandro. It's missing this class.
It's another location.
So if he wants to see this class, he can see it.
Oh.
But actually he could. Yeah.
What?
Well, I think
Alright, what did I say it was going to be about?
the acid rain, the deposition, no? Acid
Deposition. Acid deposition.
Like one.
Now the reason why we've changed the name from acid rain is because deposition then covers dust, it covers snow, hailstones, basically things that aren't rain. But fundamentally it's the same thing. It's about how acidic materials arrive on the earth from the atmosphere. So this is what we've got. We've got acidic material getting into the environment, we'll say. Now, there's two sources of acidic materials. This is a generic two sources. There aren't actually two sources, there are far more. But there are two categories, if you like. One is anthropogenic. Anthropogenic. And the other is natural. Alright, so anthropogenic, what does that mean?
That's man-made?
Man-made. So man-made sources. Yeah? Anthropogenic, man-made. I think it comes from anthros, Greek for man.
That's important.
Man-made. And natural sources. So what we're looking at then is things that men do that produce acidity. Anna.
Okay, never mind, you just explained my question.
I've just answered your question.
Yeah.
Right, anthropogenic, things that are man-made. Obviously, the population we have at the moment on the Earth, approaching, was it 7.5 billion on the Earth at the moment.
Yeah.
That's an awful lot of people, so it doesn't take very much change in lifestyles and habits and things like that to have a large effect on the entire Earth. We're also, in many countries, we're highly industrialised. We produce an awful lot of stuff. So that's what we're looking at. We're looking at the things that are made by man that can affect the acidity of the environment. Natural sources, well, the Earth has always been highly active in terms of things such as volcanoes, weather, things like that, all of which can produce acidity. But let's have a look at the anthropogenic sources first of all. So, well, now let's look at what we mean by the acidic material. What acidic materials have we got? We're fundamentally talking about acidic gases. Right? The acidic gases are released in some way, and those acidic gases interact with water in the environment, and they produce acids. Right, so we've got acidic gases. What acidic gases do we know about?
Nitrogen.
Is not an acidic gas. Go to the bottom of the class.
Nitrogen.
Carbon dioxide.
Nitrogen oxide.
Carbon dioxide is a weakly acidic gas. Right? Well, have a look at this. Carbon dioxide is a weakly acidic gas.
Sulfur dioxide.
It's very weakly acidic.
Nitrogen.
Sulfur dioxide. What's the proper name for sulfur dioxide?
Sulfide.
Sulfur 4 oxide. Because sulfur dioxide's got the formula SO2. Another acidic gas?
Nitrogen oxide. Nitrogen. Something with nitrogen, Mr. I am 100% sure, but I don't know what. Nitrogen
Ammonia.
dioxide.
Well, in fact, there are several nitrogen oxides. So I'm just going to write nitrogen oxides. And because there are several of them, we give this the formula NOx in this kind of realm of chemistry. So this could be nitrogen dioxide, it could be nitrogen monoxide, it could be dinitrogen tetroxide, dinitrogen pentoxide.
Is there sulfur trioxide?
Well, there is sulfur trioxide, but it is normally formed afterwards. It's not one of the principal gases. Right? Now, out of these three gases, three acidic gases, carbon dioxide is clearly a prevalent substance in nature. It is produced by respiration, animal respiration. It's also absorbed by trees, by plants, in respiration. So carbon dioxide is part of a cycle, and there is a certain percentage of carbon dioxide that is in this carbon dioxide cycle, and it's fairly balanced, or it has been until recently. Carbon dioxide is produced by burning carboniferous material, by burning carbon, by burning things that have grown from carbon, such as trees and plants. And if we burn too much, then we change the amount of carbon dioxide in the atmosphere. It tends to vary from about 0.02% to around about 0.04%. That's the kind of variation in the carbon dioxide in the atmosphere. And we don't really consider that it contributes to acid deposition. It does, however, have effects. High carbon dioxide content in the atmosphere causes a change in acidity in the oceans, because the oceans act as a big sink for carbon dioxide. They dissolve a lot of the carbon dioxide, and this can affect things that with a delicate acidity balance, such as coral reefs. Mara?
No, I was thinking about carbon monoxide as well.
Carbon monoxide is not an acidic gas. Carbon monoxide doesn't interact with water. Okay, that's probably the next thing we should mention. Why are these acidic gases? How do they interact with water? So, we all know that our definitions of acids, or the simplest definition, the Arrhenius definition, is something that produces hydrogen ions in solution. And so if we have a look at these, carbon dioxide, CO2, interacts with water, H2O, equilibrium, and we get first we get H2CO3. This is could be called carbonic acid, but it's very much to the left-hand side, this equilibrium. There's very, very little carbonic acid. But what carbonic acid is, because so far, notice there's no hydrogen ions appeared here. The carbonic acid itself, the H2CO3, then gets into an equilibrium with H plus and HCO3 minus. This is the hydrogen carbonate ion. And here's some acidity. Now the hydrogen carbonate ion can further HCO3 minus, can continue the equilibrium to give H plus and CO3 2 minus. This is the carbonate ion. So we can see that these equilibria lie very much to this side. But of course, if there is any base, any OH minus, well, the OH minus will react with any H plus ions, pulling the equilibria to this side. Right? So although the equilibria is virtually 99.99% here, we can still, by adding base, make it go all the way to the other side. Now the other thing we can mention here is the hydrogen carbonate ion is amphiprotic.
With a 1.
No? What was amphiprotic?
Oh, that you can
gain
They can gain or
lose
lose.
a hydrogen.
That's right, this is an amphiprotic species. And you see that here, to go this way it's losing a hydrogen ion, and to go this way it's gaining a hydrogen ion. Now this means that it can act as a buffer as well. It has auto buffering capabilities because it can absorb hydrogen ions going this way, or it can release hydrogen ions going this way. Right? So amphiprotic species often auto buffers. They self-buffer without the need to have anything else in there. And in fact, this is what happens in the sea. The sea has a certain amount of carbon dioxide dissolved in it. Under the conditions, we can form hydrogen carbonate ions, and it tends to stabilise. If we start adding too much acid, if you add acid, what happens? We push acid in, we push these equilibria back this way, and we prevent this auto-buffering capability. Right, so this is what happens with carbon dioxide. As I said, we don't tend to count carbon dioxide as acid deposition for the simple reason that it's so prevalent in the atmosphere anyway. It's part of the carbon cycle. However, the other two gases that we have, sulfur dioxide, SO2, sulfur dioxide, SO2, this interacts with water. And we get H2SO3. Once again in equilibrium. And the H2SO3 can then dissociate to give H plus and HSO3 minus. And the HSO3 minus can also dissociate to give H plus and SO3 2 minus. This is the hydrogen sulfite ion. This is sometimes called sulfurous acid. Its other name is sulfuric 4 acid because the sulfur is in the oxidation state 4. Now this is a weak acid. So in other words, the majority of the species in solution will be sulfur dioxide and water. Very, very little sulfuric acid is made, sulfurous acid is made. However, there is an issue with sulfurous acid because we live in an oxygenated atmosphere. And in the presence of oxygen, SO2 and water and half O2, so oxygen gets involved, we can make H2SO4, which is sulfuric acid. And this is a strong acid. So now we've got sulfur dioxide in the presence of oxygen, which of course is in the air, lots of oxygen in the air. So if you put sulfur dioxide into the air and with the water vapour and the oxygen, a certain amount of it can produce sulfuric acid, which is a very strong acid. So this then becomes dangerous to the environment. And this is one of the materials that's responsible for acid deposition. clearly I don't need to put the well, what happens there. The sulfuric acid in the presence of water gives 2H plus SO4 2 minus sulfate ions. There's the acidity. Nitrogen oxides, well, if we represent nitrogen oxides by NO2, nitrogen dioxide, very, very similar. Nitrogen dioxide will dissolve in water to make HNO. This is actually going to be an oxidation reaction. I've chosen a bad one here. It's going to give HNO2 plus HNO3. We're 5 there, don't we? So 2 of those. So nitrogen dioxide changes oxidation state. This is oxidation state 4. This is oxidation state 3. 4 going to 3 and 5. And this is a case of a species being simultaneously oxidized and reduced. Does anyone know what that's called?
It's not deuterium?
No. Simultaneous oxidation and reduction is called disproportionation. Disproportionation. Simultaneous oxidation and reduction of the same species. This one species both gets oxidized and reduced in this process. But what we get here is we get nitric acid, which is a strong acid. And indeed nitrous acid, HNO2, nitrous acid, this can pick up half O2 and become HNO3, nitric acid as well. So it can get oxidized by the oxygen in the atmosphere. So here we've got a strong acid being formed. This is strong. So our nitrogen oxides, which I've chosen to represent by NO2, can produce strong acid. Sulfur dioxide can produce strong acid. And so these are the two species, these two strong acids are the real contributors to acid deposition. So the next question is, how do they get into the atmosphere? Well, we've said there's two sources, natural sources and man-made sources. Let's take sulfur dioxide first of all. Sulfur dioxide. And the major source of sulfur dioxide, believe it or not, is volcanoes. Volcanic action. Volcanic activity. Volcanic activity puts massive amounts of sulfur dioxide into the atmosphere. When they had that volcano in Iceland, Eyjafjallajökull. That's it. I think it was Eyjafjallajökull. There was it put thousands of tons of sulfur dioxide into the atmosphere, as well as the dust. So the sulfur dioxide that was put in the atmosphere then is able to interact with the water vapour in the atmosphere. It's also then, it can make sulfuric acid interacting with the dust, meant that the dust particles, apart from being highly abrasive, were highly acidic. And so if you've got those abrasive acidic particles into aeroplane motors, aeroplane turbines, they destroyed the turbine blades, which is why aeroplanes had to be rerouted during the period of volcanic activity.
Cool.
So So this is a natural source. And a man-made source is burning fossil fuels. What are fossil fuels?
They're dead animals.
Dead animals. Burning dead animals, that we always do. Not really dead animals,
I mean,
are
they're
they?
like debris from like.
Okay, yeah, so they're fossilised
Yeah.
forms of vegetation or dead creatures.
Yeah, exactly.
They've formed over billions of years. So why does burning fossil fuels release sulfur dioxide?
Because there's some sulfur.
living things
present.
have sulfur.
That's right, because living things have sulfur in them. Sulfur is one of the constituents of amino acids. Some amino acids. How many amino acids contain sulfur? Ah, you said 20. There's 21. There's 21 amino acids, not 20. 21 naturally occurring amino acids, because one's been added very recently.
Oh, really?
Yeah.
Oh, so technically.
Selenocysteine has been added. It's a version of cysteine which contains selenium instead of sulfur. That's amino acid number 21. It's implicated in biochemical processes, although we didn't know about it until quite recently. So there are 21 naturally occurring amino acids. However, I've just mentioned cysteine. Cysteine is a sulfur-containing amino acid. So if you've got proteins which are made of links of amino acids, and a couple of the amino acids contain sulfur, then logically your proteins also contain sulfur, so the living systems contain sulfur, and so the fossil fuels also contain sulfur. So when we burn a fossil fuel then, we're going to burn fossil fuels to get energy, mainly by burning the carbon content, but of course any sulfur in the fossil fuel will react with oxygen in the burning process and it will make sulfur dioxide. Now what can we do about volcanic action? What can we do about sulfur dioxide produced by volcanic action?
Not much.
Not much. Very good answer. There's nothing we can do about it. We can't stop volcanoes. And therefore we can't stop the sulfur dioxide emissions. So we have to accept this as part of the law of the land, part of the law of nature. We're going to have huge amounts of sulfur dioxide. What can we do about the sulfur dioxide produced by burning fossil fuels?
You weren't there.
I can edit it out, it doesn't matter. What can we do about burning fossil fuels, the sulfur in burning fossil fuels?
Well, I would react it with something more reactive that displaces it, and it's not acidic.
Or stop burning fossil fuels.
No.
Right, okay, let's have the possibilities. Possibilities. One, don't use fossil fuels.
Or use an alternative for fossil fuels.
How practical that is, we don't know. Another possibility.
React it.
Like neutralize.
What do you mean react it? No, I don't understand.
Like what I would do is
React what?
the sulfur dioxide with something that displaces the sulfur and it's not acidic.
When?
When it's coming out, I don't know.
Right, okay, so we could take the emissions and remove the sulfur dioxide. So we can remove sulfur dioxide from the emissions. Remove SO2 from emissions. Anything else we could do?
Use an alternative for fossil fuels.
Well, we've got that here.
Yeah.
Don't use fossil fuels.
Or like.
Well, it's logic, isn't it?
Or no.
We don't use them. We take the sulfur dioxide out afterwards.
Before?
Or we take the sulfur out before. remove sulfur from the fossil fuel. Which of the three do we choose to do?
The second one, I'd say.
No, the third one.
I'd do the first one.
I do.
Yeah, actually, you're all right. Everyone's right. We do all three, don't we? We do all three. We try to avoid using fossil fuels. We do remove sulfur dioxide from emissions from burning fossil fuels. And we do remove sulfur from fossil fuels.
What a great world we live
What a great world we live in, yeah.
Oh yeah.
Oh yeah, totally.
Now, clearly, we can't. None of the three are going to be perfect, which is why all three are done. All right, but if we have a look at number one, don't use fossil fuels. How practical is that? Well, it's practical in some areas where you've got hydroelectric energy, where you've got solar energy, where you've got aeolic energy. But in some places it's just not practical. You've got nuclear energy as well. Nuclear energy doesn't produce sulfur dioxide. But in some places that we just can't avoid using fossil fuels. At least, up to now, historically, we've not been able to avoid using fossil fuels. So we have to accept that there are some places where we're going to burn fossil fuels. Alright, so if we have to burn fossil fuels, we can then look at these two possibilities. Now, removing sulfur dioxide from the emissions. Any idea how we might do this? How might we? What qualities of sulfur dioxide might we use?
I mean, the first idea that comes up to me is neutralization.
Right, and that is the most sensible idea. Removing SO2 from emissions. What made you think of that, Mauro?
Because it's an acid.
It's an acidic gas. Yeah, it's an acidic gas, right? So all we need to react the acidic gas with is
a base.
a base. That's right. We would choose a base that's very common, a base that can be easily produced, very common, such as calcium oxide. So we would pass the emissions through, and we actually call these scrubbers because they scrub the gas, they remove the materials from the gas containing a base.
Carbon. No.
Calcium oxide. So, and the calcium oxide then, CaO, reacts with the SO2 to make CaSO3, calcium sulfite. Now calcium oxide, well, where do we get calcium oxide from? Limestone. When you heat limestone, it dries off carbon dioxide and you end up with calcium oxide.
Oh.
Right?
So like in acid rain, that's why the statues like deteriorate? Or what?
Sort of vaguely, but only sort of vaguely, because it's the kind of different reaction. Acid rain, sulfur dioxide is reacting with calcium carbonate. Yeah? The marble statues are made of calcium carbonate.
That's where I was thinking.
Right? But this is a strong base, so this is a way of doing it. I suppose in principle you could use calcium carbonate for this as well. So the systems are fairly clear. So any gases emissions are then forced to go through all these regions where they've got this lots of base. The calcium oxide reacts with most of the sulfur dioxide. We get calcium sulfite, which can then be removed and used for other purposes.
Is it efficient?
Nothing's 100% efficient, but it's not bad.
Is it expensive or not?
No, it's fairly cheap to do as well, because calcium oxide is a very cheap material. What about removing sulfur from fossil fuels before we burn them?
Yeah.
Seems like complicated.
Well, it depends really what fossil fuels we're talking about. For oil, it's not too difficult because oil is in a liquid form, and so we can actually capture that. We can distill or effectively remove the sulfur by various different processes from from oil, but from coal it becomes quite difficult. Right, so removal. Number 3, removal of sulfur from fossil fuels depends upon the fuel. Obviously natural gas is a fossil fuel as well. Natural gas, we're less likely to have sulfur in natural gas. We will have sulfurated hydrogen, that's hydrogen sulfide in natural gas, but if possible, the sulfur gets removed before. Not always so easy. Certainly for things like coal deposits, we would tend to choose coals that have a very low sulfur content. Alright, we'll leave it there. We'll go on after the break, we'll do nitrogen oxides. Anyone want to do adverts?
Es que me estresa en clase porque veo que no sale y es como, oh my god.
Come on, Mr. Tarantino, hurry up.
What a compliment.
Right. Alright, nitrogen oxides. NOx. As I said, there are lots of oxides of nitrogen. N2O, NO, NO2, N2O3, N2O4 and N2O5. So we can express all of those just by NOx. They're not all acidic.
How come if all like the N also varies from N2 or N? Like why would you only give it N? Yeah. Like why would you call it NOx if also N?
Well, here X is a half. Here X is 1. Here X is 2. X is 1.5. X is 2 again.
Okay.
And X is 2.5. It's just what this is saying is there is a ratio, a variable ratio of nitrogen to oxygen. They're not all acidic gases. This first one, nitrous oxide, is the gas that's otherwise known as laughing gas. Right? It's the only gas apart from oxygen that supports combustion. Remember, oxygen helps things to burn, so does nitrous oxide. N2O, nitrous oxide they used to call it. It's nitrogen 1 oxide, its proper term. But if you work out the percentage oxygen in N2O, which is not difficult to work out, oxygen's got a relative mass of 16, nitrogen's got a relative mass of 14, 2 nitrogens are 28, 28 and 16 is 44. So oxygen makes up 16, 44 times 100%. Whatever that comes to. I have no idea what it comes to.
Right.
36.36.
Right, 36, alright? So it's about 36, about equal to 36%. What's the percentage of oxygen in the air?
21.
About 20, right? So in other words, this is almost double the percentage of oxygen in the air. So this supports combustion much, much better than air. And that's why they use N2O cylinders in hot rod cars. So they might have they put a cylinder in there which provides nitrous oxide, nitrogen monoxide, to burn the fuel, so the fuel burns that much hotter. It isn't as obviously as good as pure oxygen, but pure oxygen would cause the fuel to explode. But this gives this gives much more energy, much more possibility of burning.
Mister, why is it called laughing gas?
Because it makes you laugh.
Really? Like,
But why?
Well, it produces a feeling of euphoria. And
like-
in low concentrations, in high concentrations, it's an anaesthetic.
What?
When I went to the dentist when I was a child, they gave me this gas to make me unconscious so they could do operations. And it is still used in the dental industry.
It's a typical video that you see of like the kids that are drugged out in the car with their parents,
But
just
Mr.
like, I just came back from the dentist.
oh, is it the mask they put?
Yeah, it's a gas mask. So it produces, in low concentrations, it produces a feeling of euphoria. It's used in clubbing as a legal high. In some places it's been banned, in some places it's still allowed.
What do you mean,
I have some
like
nitrogen oxide.
the
does that
room is
work in
filled with
the body?
nitrogen oxide?
No, you buy small cylinders of it to breathe.
Oh.
It's like you're dancing.
Yeah,
I'm pretty sure you would.
But like I say, I think the legislation is working against it at the moment because there's been accidents. Obviously, it's an anaesthetic gas. It causes problems with your brain. It can lead to collapse and death. So, in a dental situation, it's being highly controlled. You've got an anaesthetist who can check all of your vital signs. In a clubbing atmosphere, it's not being checked at all, and it can cause lots of problems. It isn't an acidic gas, first of all. Nitrogen 2 oxide, NO, is a gas that's very, very reactive. This gas is produced in certain ways, shall we say. I'll outline them in a moment. But when it's produced in the air, it reacts instantly with oxygen. This is at room temperature. This reaction is instantaneous, or very, very fast, shall we say. And we get NO2. So two of those. It's a very fast, under normal conditions, we say at RT, room temperature. So that means it's very difficult to make nitrogen monoxide. You make nitrogen monoxide, as soon as it hits the air, it turns to nitrogen dioxide. So it doesn't really matter whether that's acidic or not. It isn't, but it doesn't really matter, because as soon as it's in the air, it becomes this, which is an acidic gas. N2O3 is not that common, we'll leave that out. So let's just look at NO2 then. NO2, when this reacts with oxygen, it makes, water, it makes HNO2 plus HNO3. This is the disproportionation reaction I showed you earlier. Right? So this is a weak acid, and this is a strong acid. So in other words, if we make nitrogen monoxide, it's going to make nitrogen dioxide in the air. And nitrogen dioxide is going to react with water. So effectively both this and this, these two gases are both contributors to acid deposition. Why is nitrogen monoxide so reactive?
Oh, free radical.
Oh, very good. Good shout. Why are nitrogen compounds in general tend towards making free radicals? Why? Because they have an odd number of electrons in the outer shell, which means that nitrogen monoxide, if we draw a Lewis structure and nitrogen monoxide, well, even if we share all of the available, like this, for the oxygen, that's still going to leave us with...
Very fast.
That's still going to leave us with nitrogen's electron deficient, it's got 7 electrons in the outer shell. So this is a free radical. So it's a free radical molecule. And NO2, indeed, itself is a free radical molecule. There it is. This is also a free radical molecule. And this explains their high reactivities. Mauro can tell us all about nitrogen dioxide.
Oh, like how it's produced?
What's it look like?
Ah, yellow, no? Un poquito orange. Isn't that what it produces?
That's what you were making in the fume cupboard when you reacted the copper with concentrated nitric acid. You made dark red-brown fumes.
Yes, sir. My memory.
Your memory, which was such a long time ago, Mauro, wasn't it? Last week. Right, okay, yeah, so this is a dark red-brown gas. And it's very reactive. Now, do we want something that's dark, red, brown and very reactive in the environment?
No.
No. It causes respiratory problems. It's implicated in the development of pneumonia in the lungs. It also reacts with other chemicals that are in the atmosphere, organic chemicals particularly, to produce secondary pollutants. So it's a highly polluting gas. So, how does it get into the atmosphere? Well, I'm not going to bother with these two. Dinitrogen tetroxide is formed when two of these get together. It's actually another form of nitrogen 4 oxide, caused by this single electron pairing up to make two nitrogen dioxides joined together. But they easily break apart at slightly elevated temperatures, so N2O4 is in equilibrium with 2NO2. So effectively, when we deal with N2O4, we're dealing with NO2. N2O5, not that common. We're going to gloss over them. So how does nitrogen dioxide, or how do nitrogen oxides in general, get into the atmosphere? What about a natural source?
Decomposition.
Natural sources of
Oh, ammonia?
NOx.
Oh, never mind, no.
No.
Retreat.
Wouldn't it be maybe the nitrogen cycle?
Like cows?
Not so much, no.
Is there by cows?
No, it's just methane. I was thinking about that, but I don't know.
Well, what's nitrogen oxides a combination of?
Hydrogen and oxygen.
Nitrogen and oxygen. And where do we find nitrogen and oxygen?
In
The amino acids, etc.
In the atmosphere.
In the atmosphere.
Ah!
80% of the atmosphere is nitrogen. 20% of the atmosphere is nitrogen, it's oxygen. So all it takes is a bit of, quite a large amount of energy to bind them together. Under what circumstances do we get a large amount of energy in the atmosphere?
Thunderstorms.
Thunderstorms.
When the...
Nice.
That's on fire!
Thunderstorm, yeah.
Electric arc,
Yeah,
or electric discharge.
See you in greenhouse gas.
Electric discharges in the atmosphere effectively provide columns of incredibly high temperatures. An electrical discharge might have temperatures of several tens of thousands of degrees in the very localized point or channel where the electricity passes. And so electrical discharges are sufficient to bind together N2 and O2 to make 2NO. This is my pathetic attempt at drawing a lightning bolt. Alright, electrical discharge in the atmosphere will bond nitrogen and oxygen to make N2NO. This isn't an acidic gas though, is it? So what's the problem with NO?
That it will bind to with oxygen.
It will immediately react with the oxygen in the atmosphere. Okay. So 2NO plus O2 will give 2NO2, and then we're off, and that can then dissolve in the moisture in the atmosphere to make nitric acid, nitrous acid. The nitrous acid can react with the oxygen in the atmosphere to make more nitric acid. So electrical discharges. How common are thunderstorms?
Quite, huh?
Really? Depends on the place.
All right, in the Earth in general.
Very.
Very common. There are in the course of a year there might be 100,000 of them. There is a huge number of thunderstorms. Right now, as we're speaking, there will be thunderstorms somewhere on the Earth, almost certainly. Which means that every time there's a bolt of lightning in a thunderstorm, we're binding together nitrogen and oxygen. So it's a natural source. It's a natural source. Now, we've already mentioned the nitrogen cycle. It's quite useful in a natural cycle. The nitrogen cycle puts nitrates into the soil. So we've got the nitrogen oxides, nitric acid. Nitric acid falls on basic soil such as calcium carbonate. It makes nitrates, which are all soluble. All nitrates are soluble. All nitrates are soluble. And what happens to a soluble nitrate then? It gets taken up by the plant and used in the plant's growth apparatus to produce what? What does the plant need nitrogen for?
Amino acids.
Amino acids, that's right. So all nitrates are soluble. You get plant uptake to make amino acids. So you see the nitrogen cycle is an essential part of the Earth's cycles, of the Earth's natural balance. So we have thunderstorms produce nitrates, produce acid deposition. The acid deposition gets into the ground. The vegetation uses the nitrates to then produce the amino acids. Nearly all plants require nitrates of some kind, soluble nitrogen compounds. There are very few plants that can fix the nitrogen out of the air. Does anyone know what they call a plant? What you call a plant that can actually take the nitrogen out of the air and use it?
Nitrifying.
I don't know.
Something with ultra.
Well, they're called leguminous plants.
I'm on fire today, guys.
Give or take, more or less.
Oh, is that why they do plant rotation?
Yes.
Nice.
Oh!
Anyway.
Let's keep it your excuse today.
I'm happy.
Now, in fact, the plant itself can't fix the nitrogen. It requires bacteria. So this is an example of symbiotic growth. The plants, leguminous plants, have got root nodules in which bacteria live, and the bacteria use a particular chemical element to help catalyse the binding of the nitrogen and the oxygen. Anyone know what the element is? No, it's molybdenum.
Oh,
That was fun, yeah.
that was
almost
just about
I was just thinking of that.
So bacteria in the root nodules use molybdenum to fix the nitrogen. example of leguminous plants?
Lentils.
Yeah.
Lentils, peas, beans, clover.
Chickpeas.
Clover is a classic one. You often see, for example, in England, when you're talking about crop rotation, they might leave a field with just clover. Because the clover then will fix the nitrogen, the clover will die, and it will return the nitrogen to the soil. Right? So it will not take anything out of the soil, it will provide nitrogen from the air for the soil in the form of natural nitrates, then, or amino acids break down, nitrates, ammonium compounds, all of which can be used by the next crop of plants. Right? So these leguminous plants are examples here. Examples: peas, beans, clover, lupins.
What?
Lupins, a type of flower. Lupins. Alright, all of this is the natural sources of nitrogen, or nitrogen oxides. What about the baddies? Anthropogenic.
Fossil fuel, cars. Yeah.
The usual.
Well, think about what was needed to fix the nitrogen naturally. Electrical sparks. Where do you find electrical sparks?
Anywhere.
Electricity lines.
Not so much. Where do you find a regular, repeated electrical spark? In a car engine. Car engines, not diesel cars, but ordinary petrol car engines. Petrol car engines, every time the piston compresses the petrol air mixture, a spark sets it off. And that spark then will bond some of the air, will bond some of the nitrogen in the air to some of the oxygen, and so every cycle, let's say a 4-cylinder car, which is just ticking over, it ticks over at 10,000 revolutions a minute. So that 10,000 times 4 is 40,000 sparks a minute for one car. And that's if a car's not driving. If a car's driving, it will be doing 30,000 revolutions a minute. So 30,000 revolutions, that's over 100,000 sparks a minute. Now you multiply that by the number of cars there are on the world.
And minutes.
So a single car, a single petrol car, at 30,000 revolutions per minute produces over 100,000 sparks per minute. And every one of those sparks will produce a tiny amount of nitrogen oxides. But as I said, it doesn't take a genius to work out that we're talking about a minute there. In an hour, we've got
600,000.
6 million.
Okay.
In an hour, we've got 6 million sparks from one car. How many cars are there in Spain?
Millions.
A lot.
Millions. There'll be millions of cars. There are what, 50 million people. Let's say
petrol.
Right, petrol. Yeah, 50 million people. Say it would be reasonable to say there's a million cars, wouldn't it? Reasonable.
More.
I would say, but some of them be diesel. It would be reasonable to say there's a million cars. So each car perhaps operates for 300 days a year. how many hours for each car. You can work it out. You could put together a sum and you will find absolutely fantastic amounts of nitrogen dioxide are being produced. So considering the vast number of, shall we say, car hours driven per year, this contributes a huge amount of NOx to the atmosphere. Now, we are actually privileged to live in Madrid. What happened in Madrid last Thursday?
Oh,
You can only drive at 70 kilometers per hour.
One of the things we couldn't do, you were not allowed to drive on the ring road more than 70 miles an hour. What else?
And los días pares, you had to drive like a car that had not like a median number. Yes, my dad is doing that.
No, in Madrid.
Not in Madrid.
No, they couldn't park in the.
You were not allowed to take your car into Madrid and park in the blue parking zones to restrict. In other words, what I'm saying here is measures are being taken in Madrid to reduce the amount of cars in the streets, to reduce the amount of car usage. Why specifically at the moment? Because levels of pollution are high. Why are levels of pollution high in Madrid at the moment?
Because it hasn't rained.
Yeah.
Because not so much the rain.
The temperature is high.
Or the wind, I mean.
Because there hasn't been any wind. Madrid is in a bowl. It's in a depression between 3 mountain ranges, which means there is a tendency for the air to settle in this particular region. The mountain ranges stop the air from moving out. So the air gets trapped in this particular area. And if we have conditions without rain and with sunshine as well, because the sunshine will produce secondary pollutants, the amount of nitrogen monoxide or nitrogen oxides that are produced, NOx that's produced, will make the air particularly unbreathable, resulting in lung problems, diseases, and other effects. Right? So we're actually here witnessing the effect of cars producing nitrogen oxides. So what can be done about it?
Maybe public transport costs could decrease.
Yeah.
No one has to get somebody next generation.
They already are, but
Is there in France when the pollutions turn really high, they make public transport free?
Right. So what you can do is you can have political legislation to reduce the number of cars. You can politically reduce car use. Whether that by making public transport free, by doing what they do in Paris and having as you say, even numbers and odd numbers, which they do in Paris.
Ah, they do?
Yes, they do, even numbers and odd numbers. So one day you can drive a car with an even registration, another day you drive a car with an odd registration. That by making multiple occupation of a car cheaper, like the bus vow they've got on the Carretera de Coruña. So if you've got more than 2 people in the car, you're allowed to use the central reservation. That encourages people to have more people in the car, therefore less cars. What else can be done though? Let's think about more chemically, what else can be done?
Well,
diesel.
Yeah, diesel.
Well, diesel's got its own problems that I'll go to in a minute, but we don't want to be encouraging diesel.
Not having the spark.
Electric.
Well, that's
electric cars.
all right. Cars without fossil fuels.
Hybrid.
Hybrid cars.
Hybrid, yeah.
Or directly, electrical.
Hybrid, electric cars.
Is that the future?
What else?
Maybe you do the same as with sulfur, like neutralize it?
Sort of. You're on the right lines.
You bind it with something.
Okay.
Come on, we actually probably know the answer to this, but you just haven't worked your way through it.
Oh,
It's going to be made in the engine. How can we stop it getting out of the tubo de escape? How can we stop it getting out of the exhaust pipe?
We can collect it.
You can
We
dissolve
can
it in water.
Yeah, we can dissolve it.
No.
you could add hydrogen.
What do we put in the exhaust pipe
Water.
to prevent emissions of bad gases?
I don't know.
No?
I don't know anything about cars.
A catalytic converter. You've never heard of a
Oh,
catalytic?
yeah.
Sure,
I
one
only-
word S.
Ya, siempre dicen eso, pero nunca sé qué es lo que hace.
I've never seen one.
It's always mentioned in my house.
In your house?
Te lo juro.
A catalytic converter. What a catalytic converter does is it takes the exhaust gases that are coming out of the car and it reacts them with, it uses a platinum or rhodium catalyst. So we have, for example, one of the gases that comes out of the car is carbon monoxide. One of the gases that comes out of the car is nitrogen oxides. NOx, one of the gases that comes out of the car is water from burning the fossil fuels. So a catalytic converter might take these and it will take oxygens, give them to the carbon monoxide to make carbon dioxide, and it will leave the nitrogens on their own. So this is a catalytic converter. Usually platinum, rhodium. Sorry, RH rhodium, not RD. RH, platinum rhodium. Transition metal catalyst. There are other types as well. This is just a simple, this is just one, there isn't one particular equation here, there are lots of different equations. This is just an example of what goes in. Carbon monoxide, nitrogen oxides, or what comes out, carbon dioxide and nitrogen. Is nitrogen a pollutant?
No.
No, because obviously it's 80% of the air.
Yeah.
Carbon dioxide, well, carbon dioxide, yes, that is a pollutant, but not in terms of acid deposition. It's just carbon dioxide is a pollutant in terms of
Greenhouse.
the greenhouse effect. Yeah. All right. Is this 100% efficient? No. If it was 100% efficient,
We would be happy.
then we wouldn't have a problem with nitrogen oxides. If you go to a high place in Madrid and you look towards the horizon, you will see that the horizon is reddish brown. You will note that reddish colour, and that reddish colour is because of the nitrogen dioxide.
Sí, pero lo veo.
Desde el desarrollo